Now we are going to talk about signal-to-noise ratio. We are interested in sending a signal, something useful information from one place to the other. Unfortunately, we not only have signals, but we also have noise around us. And this happens in a normal conversation, in the world that surrounds us regarding sounds, but also in communication systems. All communication systems at the end need to work with a certain distance from signal to the noise that is surrounding you. And this is an important parameter, is just the signal-to-noise ratio. Sometimes you will see it with the acronym of SNR. How is defined? Well, it's simply defined as the ratio of the signal power to the noise power at the receiver. And this is a very limiting parameter in many, many systems. For instance, in a mobile communication system, where you have some receiving antenna that is moving away from the base station, what happens is that as we just go away from the transmitting antenna from the base station, the signal decreases because we have seen that there's a propagation loss, the 1/L naught we have talked about. And there will come a moment where the signal becomes so weak that now you have noise around that it no longer you can have a reliable communication. There's a threshold that you should not pass, otherwise your system is not going to work well. So we have to talk about noise briefly and see the sources of noise. We have talked about signal before, now let's talk about noise. The antenna is in the space and will be catching all the noise that is around and could be produced by many different things. If you are home, maybe you have lighting, you just turn off the lights on, off, you have appliances, and you have all kind of elevators, electrical, we live in an electrical world. So this is really going to produce a lot of noise around you, but in most of the cases is produced by man, it's a civilization-induced noise. In some other cases, for instance, when we look at the sun, we see light, but there also will be catching a lot of radio waves. So there could be radiation from the atmosphere or from the sun, the moon, and the galaxy. That's one of the sources of noise. But also, if you have an antenna close to your body or looking to the earth, you will also be receiving power, which most of it will be in the infrared, but still we will have some tails that come to the radio frequency bands. So those are some forms of noise, but that's not the only one. The second source of noise, we normally don't call it noise, we prefer to call it interference, because it's produced by other communication systems and we could act on them just to increase or diminish those values. And in this case, that means that we are all using systems that are sharing some common parts and they could be inducing signals on the other. We call this interference. This could be just inherent to the communication system or could be intentional. When it's intentional, we normally call this jamming, because you are just trying to perturb and disturb the other communication system. There's also thermal noise produced by cables, connector losses, and there is also noise that is being produced by our own electronic equipment. And the one that is especially relevant is the noise at the receiver. The noise at the transmitter side is not relevant, because normally the transmitter is a very high power system and noise is quite low. But on the receiver, we have a problem because the receiver is normally receiving a very low power level. That means that noise could be close to the system. And in fact, there are systems where the signal is buried in noise. For instance, your GPS signal. If you try to see a GPS signal, you won't be never seeing it because it's buried in noise. And it's only after processing that the receiver could bring up the signal on top of the noise. Let's start with antenna noise. And the antenna just receives all the signal plus noise that is falling on the same bandwidth that the antenna is working. This noise power we associate normally with the noise temperature of the antenna. And this noise temperature of the antenna is just the temperature at which we will have to put the resistor to deliver at the antenna port exactly the same noise power. It's an equivalent term. It's an equivalent noise temperature or noise power. And if we associate this with thermal noise, it's Boltzmann constant times the antenna temperature and the bandwidth. That doesn't mean that the antenna is at that temperature. That will be an equivalent temperature that will deliver the same power. So remember this. If you write this number in decibels, in log scales, you have 10 log of those three terms, and you have the sum of them. And that's the value. This is the value for Boltzmann constant, and this is the bandwidth. Here on the right, you have a representation of typical noise temperatures in terms of frequencies. And here you have a log scale. It's 10 to powers that increase and increase and increase. And those are low frequencies, radio frequencies, typically around broadcasting. And you see that there's plenty of noise around. One of the main sources at low frequencies are storms, electrical storms, thunderstorms. They are being produced and travel a long distance across the atmosphere. But if you increase the frequency, and here you have 1 gigahertz, 1000 megahertz equivalently, then things are really good from the point of view of noise, because the noise is typically bound between two values. 3 kelvins, which is just the minimum noise you will have in the universe, in space. It's called the cold sky. When in the night you look at the sky and it's a black night, there's nothing, a clear atmosphere, you will see just a few kelvins. This is just the remaining of the Big Bang. And it's also more or less bound, if there were not other sources, by the Earth temperature, which is around 300 Kelvin. This depends on the temperature, but more or less is that value. And if you look at here, you will see that this is a window of very good atmospheric propagation and also of very low noise. This is one of the interesting windows. There's a second one in the spectrum, and it's the window that is really associated with the optical wavelengths we see. So our vision has also adapted very well to another atmospheric window where the losses are really low. And this is why we call this the RF, or the microwave propagation window. Now, depending on the system, depending on the antenna pointing, you have noise captured by the antenna. And we represent this. Now, what happens when the antenna, if there are losses on the antenna? And remember, this is the antenna efficiency that takes into account the losses. Then, if the antenna is lossy, we capture noise from the space, and just a little portion of this noise will be absorbed by the antenna, and the remaining, and this is the efficiency, will pass. So we have a little decrease in the noise level. But the problem is that we add noise. And the value of noise we add is dependent on the physical temperature. We call this the ambient temperature of the antenna, the bandwidth, and now here we have 1 minus the efficiency. So if the efficiency is very close to 1, practically the noise we receive is just the antenna noise, and this will be very small. But if the antenna has losses, then this really number could be comparable to this one, or even this one could be much larger than this one, because remember here in low frequencies. So you have to deal with this case in some instances. But if the antenna really doesn't have losses, then you may go just to this value. If the antenna and the transmitter are connected by a cable, then you have to take into account the cable losses. And the expression is similar. We now substitute the antenna efficiency by the cable losses. So here we have the noise captured by the antenna and delivered to the cable. Then we have the cable losses. That means that the power at the output will be the one we had at the input and the loss term here. But now we have to add noise. And the added noise is, once again, Boltzmann constants, the ambient temperature, the bandwidth, and 1 minus the losses. And now we plug this into this, and this is the total noise power we have. So now we know the power, we also know the noise added by the antenna. If there are other terms, connection terms, we have connectors that have losses, other terms, you have to take them into account. Just to briefly comment on the sources of noise, here you have some data taken from an International Telecommunication Union, ITU report, on man-made noise. Here you have frequency in megahertz. This scale goes to 300 megahertz. And here you have a log scale, 20 dBs, 40, 60. And this is just the median value for man-made noise power, depending on different environments. I have superimposed on this plot here that this is 10 times the reference temperature, 290 Kelvin, so this is about 3000 Kelvin. Here you keep multiplying by 10 every time you go up. So this is 10 million times T naught, and so on. And here you have different environments. This could be a residential area, a business area, a rural, all depends. And this dashed line is just the extragalactic, or if you want the galactic noise, let's say the extraterrestrial, the galactic noise for average values. So those are mean values. So don't take them as exact values. Depending on the environment, this could be changed. And this takes into account that part. But also, and this is the most relevant term in many, many cases, we have spurious emissions where, for instance, a microwave oven is nearby and could be also radiating, or we have communication systems that share the channel. They are open to use, for instance, Wi-Fi and Bluetooth. Here you have to live with other users that they have some limitations on power or on the bandwidth they can transmit, but at the end they are using the same channel and they will be interfering with you. So this is something you have to take into account in this case. Once you know those terms, then you can proceed and you can in some way add new terms. And an important one in the receiver is, since the signals are so weak, you have to amplify the received power. And we have to represent now a typical amplifier here. An amplifier is characterized by two parameters, the gain and the noise factor or noise figure. How is this defined? Well, since any circuit we can build normally has resistance and terms that could add losses inside, that means that this receiver will be adding noise. And we can lump together all those source noises in the circuit as an equivalent noise temperature or a noise factor. And this noise factor is defined as the ratio of the reference temperature plus the added or equivalent noise temperature divided to the reference temperature. In some way, it's just the measure of the noise added by the receiver. And it's equal to this ratio. Normally, we use two terms that are equivalent, either the noise temperature or the noise factor. And the added noise by the amplifier translated to the input is KTB. Sometimes we use the linear number here, the noise factor. Sometimes we use this number in decibels. And then we call this the noise figure. We normally use the same letters. Sometimes you will see that we use NF, but this is just the way to define. And by the units, you will know if it's linear or is in log scale. And now, this is the log, the model for the amplifier. We have the input noise, the one that is entering the amplifier, and here we have the added noise in terms of those parameters. And the reference temperature is taken as 290 kelvins. Now the output power will be the noise at the input power times the gain of the amplifier, and the added noise at the output will be also referred to the input. That's why we put here the gain. So the sum of those two terms gives you the noise power at the output of the communication system. Normally in receivers we have more than one stage, so that means that you have a cascade of amplifiers. The critical one is the first one, and this normally should be a very low noise stage. Here what you try to do is to amplify with the minimum added loss, added noise possible. And when you have a cascade, and you write here the parameters, you have the gain of each stage and the equivalent noise temperature or the noise factor, all in linear units. And now for the whole system, for the cascade, for the set of n elements, the equivalent noise is just the first stage noise temperature plus the second one, but look at the second, since this has to be referred to the input, has to be divided by the gain. So if those stages have gain, that means that those terms we are here are becoming more and more irrelevant compared to the first one, which is the critical one. This is for the equivalent noise temperature. This is the equivalent factor, noise factor for the whole chain, for the cascade of the n elements. So now here you have the rule for all the receivers. You normally need amplification, but you have to be very careful in the way you just divide the gain into different stages. You always try to have a very good one from the point of view of noise at the beginning, and then you could keep adding gain without having to spend a lot on getting a very low noise from those amplifiers, because they will not be really relevant in the final figure of the whole cascade.